before we start talking about polar functions, we have to understand what goes on with regular functions, like y equals f of x kind of things. Um, Now, you're used to getting graphs, but I would like you to imagine a function f of x, like the one that is pictured here, not as the graph itself, but rather as like a point moving through space along that path. So imagine the function is, the input is these lengths, right? For every length from here to the moving green line, like say for this here, f of this length equals this length. So f of this number is this, and f of 6 looks like it's almost about 3, and f of 7 is about 4, and so on and so on. And so this picture gives the inputs and outputs as you travel along the input axis. So it sketches out the entire thing. The result is this, and I can animate that. But it's a good idea if you really understand this thing for what it is. It's not a static graph that's just sitting there, although you could interpret it that way. But rather, if you're going to understand polar functions, it's better that you understand it as a two-dimensional kind of a motion. So this red dot has two-dimensional motion. It's moving to the right always, and as it does so, it's moving up and down according to what the function says to do. Now, there are simple functions and there are very, very complicated functions. I chose this one because I thought it just made a nice curve. It shows that the y can go up and down and up and down, and it can be 0 and it can be negative. And when it does all these things, this is what happens. Now, we're used to what this is, so this is really nothing new. But another view of this, which I like, is the partial sketch view, where this shows it tracing out as the x's go through their own cycles. So this is what's actually happening. We're used to just seeing the final result, but this is what's actually going on. So this is a typical rectangular function. Right? Y is a function of x. And we got to look at it this way before we start understanding what happens with polar functions. And this is what the grid looks like for polar functions. Instead of it being boxy, right, there's these squares all over, it's circles. Now, the way that these functions are defined is the input is not an x value, okay? It's not a distance from the origin this way. Rather, the input is an angle theta. Now, theta I have marked out here, so you can think of this angle here as being the input, and I have a couple of these plotted out. So this is an angle of 0, and then 90, and pi, and 3/4 pi, and you can keep on going around as many times as you want. But these are the inputs. So what's actually spinning here is we have a number line that corresponds with whatever angle that I choose. And the function itself is there's a point on this line that is moving around as the angle turns, as this number line turns. And what we get out of this is every angle corresponds with some distance away from the origin that this point can be. So before I actually animate it and get into it, I want you to think about this thing turning, and at the same time this is moving up and down, sliding along the axis. It can be positive out here. I have the orange marked out for where it's positive and the green marked out for where it's negative. So the output is this length. So these are positive outputs, these are negative outputs, and everything is relative to what the angle is. So for example, if we have an angle over, it's like right now, positive is up in the first quadrant, negative is down in the third quadrant. But that's only for angles that are inside here. If the angles terminate in the third quadrant, you get just the opposite. Now this is considered the positive direction, and this is considered the negative direction. As I have it drawn, the green is always the negative direction. So that's basically how it works. What I'm plotting out now is this is just this is like a constant function. First of all, every polar function has an analog in the regular function world, which we call the rectangular world. All right, the constant function in this world is just a horizontal line, right? For every x value, there is a unique y, but the y is unchanging. The y is always the same. So this is what a constant function is in the rectangular world. In the polar world, the constant function makes a circle. So we have y as a function of x here. In a polar function, you have r as a function of theta. So this distance r is a function of the angle, but the constant function says that the r is always constant no matter what the angle is. So this is the graph of what that looks like. R is just moving around as the angle goes on and on and on. It's unchanging. So this is the analog of a constant function in the polar world. Now, before I show the graph, I want to show what such a function would look, what a non-constant function typically looks like. Just like in the rectangular world, where you can sort of get an idea of what the function might look like without showing the actual graph, I want to do the same thing in polar before I show the actual graph. So I have a function programmed in there, and I'm going to set it in motion, and watch this length as this length changes, right? The angle's changing, and the radius is decreasing 0. This is where it's negative, 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 bottoms out at negative 1/2, back to 0, and then grows positive 1/2, positive 1, still growing, positive 1.5, maxes out there, it looks like, then it starts to come back in again. So this is how all polar functions are plotted. This is always happening to one extent or another. The axis, so to speak, goes around and around and around, and as that happens, this length is always changing. So let me show you a plot of what it's like when it's all connected. Here's that same function that we just watched. So I'm having it leave a trail, and it's plotting out what the thing looks like. So the R is coming in. Now, it's tempting to watch the actual curve unfold, and it really is kind of mesmerizing. But what's really going on is it's all about the length of this arm, right? The shape is formed, let me get in there. The shape is formed by what the arm is doing. So it's making it go, as the R increases and decreases, it's plotting out this shape. And it happens to retrace itself. This thing is a self-tracing curve. Let me start that up again now that we can see it. So it starts out, the R is growing, and then it maxes out, and then it's coming back in. And what's going on here is this particular function that I have entered in is a periodic function, and periodic functions are going to repeat themselves so on. Just like you see the same shape in a sine wave over and over and over again, such is the nature of repetition that these polar curves happen to retrace themselves after a certain point if they are periodic functions. So this one goes, all we have to do is, here you go, watch the angle. So this orange angle here indicates how big the angle is. So we go from an angle of 0 to 90 degrees to 180 to 270, and when we get to 360 or 2 pi, that whole thing is finished. All right, the entire graph is traced just in one full rotation. For angles beyond that, it just retraces itself again. And I think most of these happen, like most polar functions, they're going to be self-tracing after so long. But this is how it goes. Now we're going to start off with a simpler one so we can get a handle on it, just to try to familiarize ourselves with how it works, and then we'll be well on our way to, you should have an understanding of how these things actually work. So a simple place to start with these is with r equals sine theta. All of these curves have r as a function of theta, like y equals x squared plus 2. These things are r equals, say, sine theta or 2 plus theta. R is a function of theta, so theta is like the x. Now, I said that there's always an analog in the rectangular world for all of these functions. So what I'm going to do is plot r equals sine theta. Now, to get an idea of how that is going to play out, I'd like you to take a look at this. Imagining that this is the r I'm sorry, this is the theta axis here. So these are the possible angles of theta, and these are the possible heights of r. So this is the this is the r axis, theta axis, and this is r equals sine theta. This says that as theta goes from 0 to right here pi over 2, the r goes from 0 to 1. So that is going to play out. Watch how this black rod goes from 0 to a height of 1. If we plot that up in polar, if we have r equals sine theta here, at the angle of 0, the sine of 0 is 0. So what gets plotted is, let me come out here, what gets plotted is the origin. Right, this point here, 0, 0, corresponds with 0, 0 here. An angle of 0 and a radius of 0 plots this. Okay, so we'll animate it, and we go from an angle of 0 to, as we grow, the angle grows up to, see how the r is increasing, just so you're not paying attention to how the curve is drawn. Pay attention to this black line along the axis. So it's growing to, as the angle goes between 0 and 90 degrees, r goes from 0 to 1. And so far, we've plotted this much of it. We stopped there. That's the first quadrant. And then what's going to happen in the second quadrant here? Well, if you look at the other graph, you can pretty much reason that it's going to start at 1, where it currently is, and it's going to shrink down to 0 by the time the angle reaches pi, or 180 degrees. We're going to be back at the origin again, back at the pole, as we call it. So I continue to animate this, and then that's exactly what happens. This black length is decreasing to 0, and it plots a perfect circle. And then what happens next is pretty interesting. Now, for angles beyond 90 to 180 degrees, the r goes negative, but the same basic thing is going to happen, right? It still has this shape. The same thing is going to happen, but the r's are negative. So what's going to happen is it's going to retrace itself. Right? If I keep going, increment this, keep on going, you see, if you watch the whole thing unfold, first it's in the orange region here. Get in there a little bit more, and then after that. Alright, so it's coming down, the r is shrinking, and by the time it gets into position, now they change places, and the green is over here, so this is negative. R's are all negative over here, and it retraces that same pattern out. And so this happens to make a perfect circle like that just retraces itself over and over again. And this is a good intro one, because it shows you how the r increases and decreases and goes from positive to negative, and yet stays in one single configuration here. But as it keeps going around and around and around, r goes from positive to negative, just like this, in and out, in and out, in and out, over and over again, and it plots up this circle. Now I want you to contrast that with what happens when I put in a different graph. This is y equals sine theta plus 1. So it's going to make a completely different graph. In the x and y, all it does is take the old sine graph and moves everything up by 1 unit. Now, with the effect that that's going to have in polar is, it's going to take all the former r's that we used to have in the old circle graph, it's going to take all of these, and it's going to add 1 to every one of these radius lengths here. So what used to be here will now be increased by a length of 1. What used to be 1 will now be out at 2, and it's really going to distort the graph in an interesting way. So, but let's see what should happen with the radius as the angle goes around. According to this, it's going to start out, an angle of 0 corresponds with a radius of 1, and then by 90 degrees it's going to grow to 2, and then when it hits 180 degrees it's going to be back at 1 again, and then something interesting is going to happen. It's always going to be positive, and as it goes further down, then it's going to reach 0. So I'm not exactly sure what's going to happen with this when I graph it, but I know at least I understand how it's going to work. The r goes from 0 to 2, back to 1, and then shrinks down to 0 by the time we've gone. This is the third quadrant here. By the time that we've gone 270 degrees around. So let's see how that plays out. So here it is. It starts at 1, and it grows. growing, growing, growing. This line is getting longer and longer and longer. We said when it reached 90 degrees, it reached 2. There it is, and then it's coming back down. And then it was 1 again. Right? Notice we're still well into the red region here where it's positive. Keep it going, and then it shrinks to 0 when it reaches 270. Straight up and down, it just pauses right there. And then you could probably figure out what's going to happen after this. So at this point, we are here. And then as the angle plays out through the 4th quadrant, it's going to return back to where it originally started. See that? It's going to link up with where it started from. So it's going to come back down and retrace that shape. And that's how that works. So once again, we get the retracing of itself, and that's what happens when you take the radius and you add 1 to it. Now, to finish off, I just want to do something kind of goofy. I have a trig function in here. I just want to make the radius just oscillate like crazy, just go up and down, sort of unpredictably. It's still a periodic wave, but I want to make the radius go up and down like this as the angle goes on and on and on. So I have this crazy trig function in there, and I just want to put it in, have a little bit of fun with it, and see how it sketches out. So this is making the radius bounce back and forth, up and down. Speed this up a bit. Alright. So this is how it works, just the radius. You can see from here that the radius is always positive, so that means we're always going to be in the red region here, and it's periodic and links up with itself there. So that's the complete graph of this, and it's just going to retrace this over and over again. It's neat, it kind of has a symmetry about a line here. If you look like this or like this, right? You can make a lot of neat curves with these polar functions. And I encourage you to go to click the link below and play around with it. Get nosy with see what kinds of functions that you can make. Now, this video is not intended to be an exhaustive treatment on polar functions, but it's just to give you an idea of how these things work, so that when you find them in class, or maybe you see them on the SAT or something like that, you're not totally taken off guard, and that there's a reason behind, and that you understand the reason behind why these things are doing what they are doing. And I just want to end off with a couple of curves that pop up a lot in textbooks, like this guy. This guy is r equals cosine 3 theta. So it's a cosine wave, and it's got a heightened, it's got a high frequency. And how it rotates is like this. It's rotating in and out like so, and it retraces itself over and over and over again because of this is cosine 3 theta. If I plot cosine 4 theta, 5 theta, 6 theta, 7 theta, it makes these different, what they call rose petal curves. So this is 3 theta, this is 2 theta, here's 4 theta, 5, 6, because it's retracing it in. Here's the whole thing. I can have it trace the full curve at once, the whole thing, so we don't have to actually watch it being made. So that's what you're left with. So this is cosine of 6 theta. You could play around with it, say cosine of 6 theta, say times sine theta, and that is going to distort the wave a little bit more, but it's cool to watch it trace out. So again, I encourage you to just get nosy with these. There's a cosine 6 theta sine of 2 theta, cosine 6 theta sine of 3 theta, cosine 6 theta sine of 4 theta, 5 theta, 6 theta, 5 theta again. I kind of like that one. 7, I like that one too. 8, right? Play around with this. See what neat things that you can make. You don't have to just stick with sines and cosines, but they often, combinations of those tend to produce the nicer graphs because they're nice and predictable and periodic at some point. So I hope that you got something out of this video. Check the link in the description to go play around with it in Desmos, and thanks for watching.